Okay, great. So let's come back now. So we basically have all the Feynman rules we need to understand weak processes. And so we could, in principle, calculate right, all of the different processes we want for weak interactions. Let's talk about a little bit in the last bit of class here. Let's start talking about electroweak unification. This is basically how do we merge the theories for electromagnetism and weak interaction into one theory that I don't have to carry around two separate theories to describe everybody. And we're gonna see that this has been done successfully, that there's one theory that can describe both things, but the requirement that's going to come out of this is that, right, that we have these so right, here's the weird thing about unifying the theory is that we have an electron, or sorry, we have a photon, and we're going to have a Z, and we're going to have the two charged leptons, right? The charged W's, the W particles here. And the question is, how did it come about in this unified theory that the photon is massless and the Z is so very heavy? And what we're going to see is that this electroweak unification theory, electroweak theory, doesn't explain this itself. But then when you take this unified theory and you say something had to be causing the difference between the mass of the photon and the Z, if you have a mechanism to generate that, then this electroweak theory falls into place. So this leads naturally to the Higgs mechanism that explains where those masses come from. So we're going to write down electroweak unification, and the questions that are open at the end of this unified theory are what led people to develop the Higgs mechanism. And we'll talk more about Higgs mechanism next week. Okay. So what does our electroweak unified theory need to be able to describe? It needs to be able to describe the difference. Okay, needs to describe the difference in coupling between, right, between W, Z, and gamma. And we've seen already that the difference doesn't really come in the coupling strength at the vertex term, but it comes in the fact that, right, comes from, we know the answer to this one, comes from the mass of the W and Z. Okay. And so that immediately we're going to see leads to the question, well, why is there that mass difference? Why is the Z heavy and the gamma massless? That's a natural question that we would hope electroweak theory could answer. And the answer to this is going to be the Higgs mechanism. So we'll talk about this as we go along here. What other things are different between the weak interaction and the electric interaction? Well, weak interaction is a V minus A coupling at the vertex. E and M is a pure vector coupling. We've seen that several times. We've seen that now over and over again. Okay. So here's how we're going to handle this, or here's how people wrote down a unified theory for these things. We're going to start by defining a new type of state. So we're going to start with this bullet here. We're going to work on this bullet. How can we write down a theory that is vector minus axial for some of the particles in the theory and pure vector for some of the other particles in the theory? And here's how we're going to do it. We're going to define a state that I'm going to call a UL state. That's going to look like 1 minus gamma 5 over 2 times UP. And I'm going to define a V state that looks very similar, but it has the plus sign here, VP. Okay. So again, the U's and V's are our normal spinor states, but now we're defining this special version that we're gonna call the left-handed, right? So in a certain frame of reference, this is just picking out the left-handed component of our ordinary spinors. And right, with this notation, we could ask, well, what is UL bar? Okay, UL bar is just UP, and it switches the sign on gamma 5. If you work through the math on this. Okay. And there's a few relationships you can find. You can find that if I have gamma times 1 minus gamma 5 over 2, this thing is equal to gamma plus gamma 5 over 2 gamma mu. And there's another relationship that's going to be important, that if you calculate 1 minus gamma 5 over 2 squared, that this is just 1 minus gamma 5 over 2. These are just mathematical relationships that you can find if you work through the vector algebra or the linear algebra on these. Okay. And so why is all that useful? Because then what I can do is I can write down a theory that starts to look a little bit more like the beginning of a unified theory. Okay. Where I have the E coupled to a neutrino through a W, say a W minus, if I want to describe this current, right? If I want to describe that current, I need the vertex term, and I need the bits for the different the arms of this diagram here. Turns out I can write it down like this then. I can write it down, well, we know that it should be something like the neutrino side, right? So if I had different states here, it should be something like, say if this was, we call this, say, leg 1 and this leg 2, it should look like U2 bar gamma mu gamma, times 1 minus gamma 5. It should have the V minus A form, and then U1, right? Something like this. It should have this structure here. But we can use our new notation to combine this guy, right? We can basically move it through the gamma. We can swap this and use the relationship we see above to trade the places of those and change the sign in front of gamma 5 and connect that 1 minus gamma 5 with that U bar, and we can write it down something like this. That it's that neutrino state, but I'm going to call it the left-handed state times gamma mu, and then I'm going to call this other one, say, the electron state, just to help us see it. And now notice here that I've written an L on both of these terms, right? It means both of those states are multiplied by this 1 minus gamma 5 term, or 1 plus gamma 5, right? And I can pull that apart because I saw that if I square 1 minus gamma 5 over 2, I just get back itself. So I can always split this right into two pieces here, right, with the appropriate factors of 2 underneath. And this is nice because this has all the vector minus axial form that we need for the weak interaction, but it starts to look more like the rule we wrote down for electromagnetism, right, where I just have the states and then I have the gamma matrix acting as the vertex element here. So one of the first tricks here is I'm pushing this 1 minus gamma 5 bit, the thing that introduces the axial, right, the V minus A behavior. I'm associating it now with the states instead of with the vertex. Okay, so that's one of the first tricks that led people to start seeing how they could unify these theories here. because we know that an electron coupled to a photon, say, right, the current for this thing, say the E, right, the electromagnetic current for this thing is like electron is purely vector. Right? And I could write this down now in terms of those states that I saw above here. So I wrote down a left-handed state. I could also write down a right-handed state. You are VR, sorry. Right, what would they be? They would be the other handed state here. Right, they would be the one that picks out the other projection of the spinner. Right, and the same thing for VR. And so I could write down that this guy, right, the one that is just purely vector is actually a linear combination of the left-handed electron state coupling to the left-handed electron state and the right-handed state coupling to the right-handed state. And when I make this linear combination, right, the gamma 5 terms would all cancel out and I would be left with something that's purely vector. But again, this is starting to look a little more unified, right? You can see that the weak interaction, somehow I have only this bit that couples the left-handed particles together, whereas the electromagnetic, I can at least write it down into a set of states that look similar, but it's a different linear combination of them. Okay. And so we're just about out of time, but so we can then write down something like this. We can introduce a left-handed state that I'm going to call chi. And this is going to be a state that couples the neutrino, or that contains in it both the electron and its associated charge lepton inside of it. I'm just going to make a little doublet out of those two states, right? This little object that collects both the neutrino and the electron together. And I'm going to define two matrices here. I'm going to define one that's called tau plus, that looks like this, 0, 1, 0, 0. And I'm going to define another one called tau minus, that's just going to be defined like this. Okay. And the interesting thing now is I can build, say, the electromagnetic current. I can build that J mu E and M. Oh, sorry. I can try to build a, right, I can try to write down the coupling of, say, the neutrino to its antiparticle. So this thing that I call J minus above, right, this guy. I could try to build that J minus coupling using these tools here. And if I write that, it looks something like this. Why can I not write it? J mu minus is equal to chi bar L gamma T minus gamma L. So basically I have a way, right? So that T term is just a matrix that is going to pick out either the neutrino or the electron portion of that doublet in the appropriate way that I want to insert it. Okay. So the question is then, okay, so I have this thing, right? The question is then, well, can I write down, right, J, E, and M in terms of these matrices here, right? How would I write that down in terms of these chi states and these tau states? we're going to see that there's a way that we can do that, and that there's an interesting structure that's going to look really similar to, right? This thing is basically going to end up looking like some kind of, it's going to look really similar to some isospin doublet like we defined for the proton and the neutron, are the up and down, that there's a relationship, a special relationship between the neutrino and the electron. And I can write down a structure that's going to use that notation so that I can describe the the coupling of an electron, right? So that I can write down the electromagnetic interaction in terms of these terms. And when we write that down, we're going to see that there's an interesting implication, that automatically we're going to see that there are a set of unified bosons that describe the coupling in this theory that look analogous to the four particles in this unified theory, right? We have four bosons in this unified theory that we're trying to describe: the two W's, the Z, and the photon. And we're going to see that those naturally come out when we write down a structure, but with some interesting twists that we'll talk about on Tuesday. We'll stop there for today. So we'll finish the discussion about electroweak unification on Tuesday, and we'll also real quickly, I'm not going to dig into the details of the Higgs mechanism, but we'll do a little bit of a primer on the Higgs mechanism, at least to set the stage so you can go read more about that if you're wanting to do that. There are nice chapters in your textbook on the Higgs mechanism. And then I think we're scheduled to next Thursday watch the particle fever video. So we'll do that next Thursday. Okay. Any questions? Okay. If not, we'll go ahead